All right. So like I said, we are now beginning with the formalisms, mathematical models, mathematical structures that we will need to be able to model the AI security. One thing that I did not say in the previous lecture, probably because I skipped the last slide, is that we are now left with three layers of AI security. The bottom layer is AI space. In that AI space, there are the various AI processes that are dynamic, that we will need to model. And then on top of it is the logic, is the reasoning of AI agents, which make decisions on which the security depends. I'm sorry that I should have closed the preceding lecture with this. So we are now with this first part, which is the bottom layer of the structures, the AI space. And well, the lecture has two structures to present: channels and these bracket algebras or pregroups. And then we'll summarize what we're talking about. So where do these channels come in, and what does this AI space consist of? So now, and this is the real question, points for answers. What is the most likely next word after the word what? What might it be? Anyone?
What are you doing?
For instance, that's a possible answer. So you get some choices, and for instance, you try to extrapolate the entire sentence, the entire phrase. What an LLM is doing, it just tries to guess the next word. So what is the most likely next word after the word what? So you might go at what do you do, what is something, what are we, and so on. So suppose that we choose the word is, and then the question is the same. What is the most likely next word after the words what is?
Is it the?
I didn't understand it. Just try again.
The?
Another bunch of options. And we have these possibilities, but an LLM has probability distributions, which it derives from the frequency of occurrences of the words in its data set. So after this, you could ask, what is love? What is banana? What is true? Suppose that we take the article, which is usually the most frequent word in many contexts. And then we can ask the same question after what is the, and there will be another, what is the name? What is the area? What is the depth? We can choose what is the most likely, what is the most likely next, what is the most likely next word. And we have generated a phrase. We could add to this. Okay, so the LLM considers these words as tokens, and it considers orthographic symbols as tokens. So we could add this question mark as a token, and we would have a well-formed sentence. What is the most likely next word? This is how LLMs generate language. And as far as I'm concerned, this is how I generate sentences. I just launch into my sentence and make one word add one word at a time. And by some miracle, it ends up being a well-formed sentence. On the other hand, in information theory, what we just presented is is the stepping stone into basic theory of communication. It's the notion of the source. It's a random variable which depends on the preceding sequence of samples. So you sample a random variable and you get the word, for instance, what. Then in the context what, you sample the random variable again and you get the word is. And then in the context what is, you sample the random variable and you get the next word. What is the next word that I will say? A sequence of random variables like this is what you start. Well, what Shannon started his seminal paper about mathematical theory of communication, and better information theory textbooks also start from the notion of source. So formally, you get two sets of tokens. You can think of these big X's. The X with little plus on top of it means non-empty sequences. It is the type of non-empty sequences from the type X. And you can think of type X in large language model. The type X are the tokens. When you and I form sentences, the type X are the words. When you and I choose words, the type X are the morphemes, the letters that word is comprised of. And the relational source is just a relation between, let's say, a sequence of words and the next word. What is the next possible word? And the next word, if it still forms a well-formed phrase together with the preceding context, it is a possible continuation of that context. If it does not, then it is not a possible continuation, and then we assign to this relationship 0. So if this string, what is the next, allows the token word to come as next, then we have the relation of what is the next and word is satisfied, and we have the value 1. If we try what is the next is, that does not result in a well-formed English phrase, and then the value of that relation is 0. The relation is not satisfied. This is slightly oversimplified because things can either be related with value 1 or not related with value 0. And you and I and large language model have these more likely and less likely continuations of the phrase, so that in actual information theory and in language models, we are using stochastic sources, not relational sources, where the relation of a context, so it is this non-empty string of elements of type X, so it is x1 to xn. That is the context and the continuation. So what is the next? And the continuation would be word. It has a probability, whether it is what is the next word, or what is the next banana, or what is the next horse, or what is the next organism. Each of these possibilities has a probability, and large language models, you and I, derive these probabilities from experience. How often has some word occurred? Large language model gets its data set and it counts how many times in this data set does the string from x1 to xn plus 1 occur, which is of course fewer times than its prefix from x1 to xn. Here should be xn minus 1. So this ratio is the frequency of occurrences of xn1 in the context from x1 to xn. and that is the conditional probability of xn plus 1 occurring in the context of xn. So this probability, if you list these probabilities as rows, if you list them in a matrix, you get something that is called a stochastic matrix. It's a matrix of numbers between 0 and 1, where, let's say, rows add up to 1 in all cases, which means that they are probabilities or frequency distributions. A square matrix of this type is a source. And that is what information theory studies. So this is what I just gave you is the crash first lecture in a course in information theory. Why? Because these information sources are the meat, they are the muscles of large language models. Actually, a slightly more general concept is the meat of both information theory and of large language models, and that is the channel, where this underlying type is not unstructured. It's not just a type of anything. I said X could be words, it could be tokens, it could be letters, but they are parts of input type and data type and output type. And we have the information channel. You can think of it as a source where the underlying set of signs, of symbols, consists of input-output pairs. And there then this derivation sequence, which we had for source, which was a string of x's and the next x, or string of words, it was what is the next and then the next word. Here we have strings of pairs and the next pair. And their frequency is again, their probability is again taken to be the frequency of occurrence of the string of pairs x1, y1, x2, y2, all the way to xn plus 1, yn plus 1, divided with the number of occurrences of strings of pairs up to the n. Of course, since these the bottom strings are the prefixes of the top strings, there's more of them, namely the sequence from x1, y1 to xn, yn continued with any other pair and not just xn plus 1, yn plus 1. The part of them which end with xn plus 1, yn plus 1 are those that interest us, which tell us what is the frequency of occurrences of xn plus 1, yn plus 1. So the difficulty of saying all of this in English, I mean, it's not too difficult, but it's kind of clumsy and I need to use lots of words, is the reason why people develop this into this math notation. It's much easier to write down this conditional probability, which I have written down here, than to say it all in English. And not in this notation, in notation with PR and something. This concept goes back to 18th century, to early 18th century, even to late 17th century, I think, actually. Yeah, 17th century, not 18. So I hope you won't have trouble with it. I mean, what you're looking at here is just the notation for this frequency, which is you count how many times the string with up to n plus 1 occurs in the corpus, in the data set of the large language model. You count how many times the prefix up to n occurs. The fraction of the letter count is the frequency of the former count, and that is the probability that this pair will occur. So that's how they get to the frequencies, and that is how these frequencies stay in our head. So why do we need these information channels? For instance, and again,
I have a question.
yes,
So can you go back to one slide, please?
yes,
Oh, so you mentioned that the X's are like the sources, which is like the next word, right?
yes.
So when you say pairs, what kind of pairs of what exactly? Like words also, or
That is exactly what the next slide is coming to answer.
okay, sorry.
No, it's very good. You're asking the question which naturally comes here. Why do we need these channels? So uh, the the guessing of the next word, which ChatGPT is performing in front of us, is done by something called by an algorithmic structure called self-attention. It was preceded by the algorithmic structure called attention, and the purpose of that algorithmic structure was to do translations. So when we need to do a translation, so suppose I get a couple of words, I have a phrase, in this case in Dutch, and I need to translate it in English. The process of guessing, of translating, is another instance of guessing, not all that different from the production of the source that we've just been looking at. So if I begin with the word welke, what would be the English translation of that word? Well, it could be which, it could be what. So suppose we choose which. And then I'm consuming the next word of the phrase which I'm trying to translate, welke woord. And I'm taking into account the context, the English context into which I have already translated the prefix of this phrase. So I have translated welke to which, and I have woord. The only possibility, Dutch woord, is English word. So I just take word and consume the next word of the Dutch phrase. Welke woord lijkt? So there are several possibilities. Which word looks, seems, appears, and so on. So suppose I choose looks. Welke woord lijkt waarschijnlijk? Which word looks the most what? Likely, the most probable. Which word looks probable? Welke woord lijkt waarschijnlijk hierna? Which word looks probable after this or later? So I have translated this phrase. And then, since this phrase, which word looks probable after this, sounds a little clunky in English, then you, as the translator, will then look at your word, and you will do this before you actually utter the translation. If you're simultaneous translator in United Nations or something, and you will transform it. You will transform it into a more natural phrase in English. What is the most likely next word? And this is the higher level transformation, which shows that we actually have in our heads not only the frequency distributions over words, but also over the phrases. Because this phrase had a low frequency distribution in our head. We said it's not a natural English phrase. So we somehow store that. We don't have big enough heads to store probabilities of all possible sentences in English. So that's a challenging question. How do we know that this phrase is not a natural English phrase, and we know that this phrase is a natural? So how does that? In the first part we had this: how do I make that sentence? How do I generate it, and how do large language models generate it? Now we have a not harder, but more subtle question. How does the head of a translator from one language to the other work so that they not only map words to words, but that they then remap the phrases into natural sentences in the target language? Where do these transformations come from? All right, so the attention channels that we will be looking at are a simplified version of these information theoretic channels which I've been looking at, where where well, why can we afford this? I will get to that in a minute, but in any case, we ignore the feedback, we ignore the dependency of Y outputs on the previous outputs, which you would say in practice is out of question. How can I be translating a phrase into English without taking into account the translation which I have already made? But that is possible because of a certain miracle, to which I'm going to come in a minute. So in any case, we will be looking at channels in this format. This is the definition of a channel. It is a probability distribution between pairs of sequences of inputs and single-step outputs. And that probability is again counted in the same way which I've described clumsily and repeatedly several times. You count things and derive the relative frequency, and you take the frequency of past occurrences to be the probability of the future occurrences. So this is the kind of slogan of this part, the summary of what I launched on you so far. This is the minimal structure that we will need to use, and it turns out to be sufficient. Are there any questions? Why is it sufficient? And self-attention, so what actually the chatbots are doing when we're using is that they're taking an instance of information source, and they model it as a special case of attention channel. And this is just, you will notice, just the preceding concept of information source which I introduced. Okay, so where are we? We've got this framework where from which the language that we have been witnessing being generated by chatbots and language model is coming out. So this is the underlying structure, the most abstract and the simplest, the minimal piece of structure that will suffice for us to reason about it. So every science is determined by its space. You know, when we went to school, natural sciences happen in physical space, and it's this three-dimensional thing we had the coordinate systems and we had the vectors. And the space in which these information flows happen, the space of language, consists of these contexts, of these sequences of words, which we can then bundle together in these generative trees. So if I take all of these sequences of words and put the common parts as nodes of a tree, I will get this tree, and making my sentence consists of climbing up one of these trees. And the miracle is that when I reach a leaf, you somehow know that I have finished the sentence. And if you ask yourself, how do you know that? The answer to your question, to that question, is not only an entire science of linguistics, but it is a science whose theories have been empirically, to a large extent, disproved in front of us by the occurrence of these large language models and chatbots. Because for thousands of years, going back to Panini, literally for more than 2,000 years, all grammaticians have been telling us how we generate our sentences by traveling along some grammatical forms and by applying some grammatical rules, some rules of grammar. And we ostensibly see in front of us pieces of software which do not contain any grammatical rules and which form perfect sentences. So we have studied how sentences are made for thousands of years, and we were all the time on the wrong track, only to disprove to ourselves that wrong track by engineering trial and error, resulting in these large language models. So now we need to understand what has been achieved and how do we really generate these sentences. And we generate them by running these algorithmic channels in our heads, which are choosing leaves of these trees. So let's see how that goes. So, but in any case, the point of this slide is that you see how different is the space we are in now in studying language and information spaces here on the right, how different it is from this physical space on the left. We will have a lot to say and to use we will have a lot of use and function, and my fever really isn't very good for making sentences. It will be very useful for us to have these coordinate systems and vector spaces, which have been developed for representing physical spaces, also for modeling language. But you should not think that the geometry is the same. We will be using vectors, but we will not be in this vector space on the left. We will be on this contour space on the right. That is the message. The upshot is that there are kind of two kinds of spaces, and you can recognize these two types of spaces in your own mind. I was talking with some of you about it. I can, in my mind, distinguish two types of thinking: inner visions, which are pictures, which are recordings of things that I have seen or heard during the day, and inner voice, which is in the language. And if I need to fall asleep, I need to shut the inner voice down and to push the inner visions as fast as I can to push images, and then they transform into dreams. If I want to do algebra, then I need to shut the inner visions and I'm staring at the ceiling where there is nothing to be seen, so that this language can work fully. And the space of physical space is continuous. The space of inner voice, of information, is very discrete in a completely formal sense, which you as students of computer science are quite familiar with. And it depends on the rhythms of whether speech or algebra. And this dichotomy of our minds is reflected in the dichotomy of the spaces that we're now studying. On one hand, there's this physical space which we're recording by our senses and can reproduce as in a visions or images. And on the other hand, there's this information space, which is our language faculty, which is what they say characterizes our species, which only humans have, but animals don't. So now, on one hand, we share the physical space with animals, and we share this information space with computers. Animals can't speak like we can, but computers can. But we can also move in physical space, and computers, it's not so easy for them. In any case, so there is the geometry of places, which we have studied in linear algebra and in which we study in physics and other sciences, and there is this space of contexts in which we generate language. So that's what we're going to be doing. But it's not just our language. It's the space of context is also the language from the language of our bodies in which we build. So the language of genes is not all that different from any programming language. It has its interpreter, the ribosome. It has its execution engine, and it produces the proteins, and then just like computers start computing and interacting in a network and process data together, our cells, which consist from proteins generated according to the schema stored in our genes, then start interacting, build our body. So the gene space is an information space. It's a language space. Depending on how you present it, here's a list of actual genes, which are not all that different from the sequences of words that we produce to make sentences, sequences of sentences to make texts, or sequences of letters to make morphemes or words. Cyberspace is also not a three-dimensional physical space, but it's a space of sequences. It's more like our genes and like our language. And when you interact with cyberspace, then you're literally looking, all the caches are sequences of some records, which have standard formatting just like our genes do. A feature of languages which are not shared by all forms of information space, for instance, they're not shared by cyberspace, is that they're articulated. So a language is a hierarchy of sequences of something. So we first have sounds, and then we standardize them into the alphabet which we're using either to speak or to write. And we know that different languages have different alphabets, but every language has a standardized formal finite alphabet. And then from that, the hierarchy kicks on. So sequences of symbols from the alphabet, a subset of all possible sequences is the lexicon. Those are the meaningful words. Not all sequences of letters are elements of the lexicon, only some of them. And then sequences of words from the lexicon are meaningful phrases, and among them we distinguish some phrases which are complete sentences. Why do we articulate our speech into sentences? Well, for the same reason for which we articulate the sounds that we use to signal things into words. We don't break a sequence of digits which form a real number, but we say, oh, I'm gonna continue it infinitely long, and it's gonna denote this point in continuous space with increasing precision. So we do not break numbers into finite words, and that is why our numeral systems do not have articulation. You don't have numbers which then form sentences of numbers. But we do have sentences of words because we break them. And we break sentences so that we can continue to make sequences of sentences to form texts. So the important message here is that while channels are generating these sequences, the sequences are truncated into words, and then these words are used as the material for new sequences, for sequences of words, which are then truncated into sentences, which are used as tokens to sequence them into text. The miracle is, and the language space of LLMs, on the other hand, recognizes only one level, only the tokens. So the miracle of language, the miracle of predictive inference, the miracle which happened in front of our eyes when we met chatbots, is that all of this hierarchy emerges from something which doesn't know anything about the higher levels. It is only guessing the next word. So the miracle of predictive inference. Predictive inference is this, so the channel predicts the next word. It infers it from the previous context. Large language model, by means of predictive inference, generates strings of words. It only ever predicts the next word. And by miracle, these words fall into place to form well-formed sentences. The large language model sequences one word after the other, after the other, after the other. And like you and I, it ends up finishing a sentence. And unlike all of the numerical approaches that we have developed for engineering, because there a number is approximated better and better, and a digit comes after a digit, comes after a digit, and like the number pi, we need infinitely many digits to denote something. Our natural language goes completely differently. It doesn't approximate anything infinitely long. It puts a word after a word after a word, and then it stops. And then it starts from the beginning to make a new sentence. And then it stops again. So it's made two sentences. And then it makes another sentence. So we try to approximate something, but then we approximate something that we want to say. And then we approach it from a different direction, and then from a yet different direction. And we call that conversation. And that is a completely different approach from the space of language to transmission of meaning, from the approach that we have developed in physics and engineering, where we attempt to approximate things with infinite precision. These multiple articulations are the miracle of predictive inference that we need to, by hook and by crook, try to understand as far as we can, and to see why is this happening. So what is happening is that I'm just summarizing what we started from. There was a word, what is the most likely next word, and it ended up being a well-formed phrase. And the relationship between a context and the next word, the relationship between a sequence of words and the next step expands not only to the relationship between a sequence of words and the next sequence of words. Those of you who attempted to guess the next word were inclined to guess the next word in the context of the words which come after that. So you guessed not just a single next word, but the entire next phrase, because our mind is made to anticipate. And this predictive inference is actually the driving principle, not only behind our current explanations of how large language models work and how these large language models in our heads work, but also the leading principle of neuroscience. Apparently, not only do you predictively infer what will be the next words in the sentence that I'm now saying, and most of the time, if I stop, you will know what was the next thing that I was going to say. And most of the time, you're just error correcting if I say something that you didn't expect. But that is apparently how our eyes and ears work as well, because by fMRI they have discovered that the way we perceive things come inside out and not outside in. It's not that I see a tree and then it comes through my eyes and reaches my brain to be interpreted as a tree. But if I'm looking around the park, my brain will anticipate a tree, and by fMRI, they will find that I have recognized the tree before my eye has set on it. So this mechanism of predictive inference is the miracle of a good part of our functioning. So let's see how far we can get with it. And it's everywhere around us. It's not just that single word predictions produce well-formed sentences, meaningful text, purposeful narratives, sound reasoning. You know, you and I can argue and each of us will attempt to produce sound arguments. How will we do that? Well, you're not thinking 25 sentences in advance. You're thinking, what's the next thing that you will say? And you end up saying 25 good things because they're somehow connected and coherent. And somehow this predictive inference, saying one word at a time, leads all the way up. The top level of our linguistic faculty is our identities. Because why am I saying this? Well, any particular sentence that I may say will be interpreted by you, to the extent to which you know me, differently than that same sentence, which you would interpret differently if you hear it from someone else whom you know as a different. If one person tells you I love you, and if another person tells you I love you, that is not the same sentence. So the personal identity is the top level of language interpretation. And it goes on. Single step productions produce music. The way people play and compose music is also one step at a time. The best chess players are thinking just a couple of moves ahead, and they develop spectacular, sophisticated 30-move strategies. Reasoning again. So there's this general principle that wherever we go, we get there by kicking a can down the road. We never see much further than by where the can goes. So predictive generators, we will one of the tables will have a little exercise to explain the different presentations of channels. So we can have we will need different presentations to reason about them. We can have channels which predict a single step, and we will have channels which will predict the entire output. We will get there, I hope, next week. Okay, but now are there questions about the first part before I say why it's all not good enough? Okay, brackets. What? Yes, question.
Sorry, just a question about when you mentioned that according to like fMRI that like your brain kind of anticipate there is a tree, so, and then your eye sees it.
Yes.
But like what if it's a tree that you never seen before? Does it work the same?
No. We're receiving information. New information is defying your expectations. If everything that you have predicted and what you expect continues to happen, you're receiving very little information. So I can obviously only predict trees that I have seen. When I see a tree which I have never seen before, then I will error correct. My brain will predict that I will see a pine there, and lo and behold, I will see this Jurassic tree which has been thought to be extinct for 300 years, which no one had seen, and that will be a genuinely new information. That is recognized in my brain. Apparently, I'm not a neuroscientist. I'm just telling you a very high level bird's eye view of this predictive inference principle, which has permeated neuroscience in the last 10 years. You can Google for free energy. Believe it or not, a movement in neuroscience is called free energy. It's of course a physical principle, but a guy in London is explaining predictive inference by means of free energy, and then you can pursue there's actually extensive literature about it. But let's see what we have in our bag with these channels and what we don't. So the problem with trying to capture language productions in terms of channels is that, as you have seen here, I'm saying, so these, do you guys speak this basic language of lists and streams? I think people who have had 355 with me do, but does everyone know what are these asterisks and this plus? Anyone who doesn't remember? Okay, so we don't need to spend time on this.
I don't know what the plus means.
Plus means non-empty strings. X plus are non-empty strings. So X star is X plus the empty string. So there's a very little difference.
Oh, okay.
But the important thing is here you have non-empty strings generating a single output at a time. Here you have arbitrary lists, empty or non-empty, generating lists. And that's kind of important. Now, if you think about it, the set of lists of a certain type, it is the free monoid for concatenation. Empty list is the unit, and concatenating lists putting them one after the other is a monoid operation like addition of integers or multiplication, and which means that it's an associative operation. Addition of integers is associative because 2 plus 3 plus 7, whether I first add 2 and 3 and then add 7, or I first add 3 and 7 and then add 2, I'm going to get the same sum. And these lists are also associative. We don't put brackets in here. But language is associative. If you take the phrase rotten apples and oranges, that can be interpreted in two different ways. Either both apples and oranges are rotten, or I have a bag full of rotten apples and I also have some oranges. So how do we capture that? So there's this problem that on one hand we have channels, but the channel productions are associative, and the actual language we speak is not associative. Do I have this? So here's my favorite non-associative. What am I trying to do? I'm trying to go. I'm trying to go here. This.
One morning, I shot an elephant in my pajamas. How he got in my pajamas, I don't know. Then we try to remove the tusks. The tusks. That's not so easy to say, tusks. You try that sometime. Tusks.
Oh, simple. Tusks.
Pardon me, my name is Spaulding. I've always wanted to meet you, Mr. Chandler. As I say, we try to remove the tusks, but they were embedded in so firmly that we couldn't budge them. Of course, in Alabama, the Tuscaloosa. But that's entirely irrelevant to what I was talking about. One morning, I shot an elephant.
No. Okay. So you've just heard a paragraph of ambiguous sentences. Here's the one which... Is everyone still with me? I didn't disconnect Zoom or anything. So here's one sentence which he said, I shot an elephant in my pajamas. So you can, and you have the parsing tree above it. Do you remember these parsing trees, how we parse English grammar? We can talk about it later. Maybe we'll need to refresh it. So this is a sentence which consists of noun phrase and verb phrase. And a verb phrase consists of the original verb phrase, shot an elephant, and a propositional phrase, in my pajamas. And here, the verb phrase is interpreted that he shot an elephant in his pajamas. It can be interpreted differently by saying that an elephant was in his pajamas. So either he was in pajamas when he shot the elephant, or the elephant was wearing his pajama when he was shot. And this ambiguity is then used to realize the joke. So now, of course, to capture this partition of the phrases, we can transform this tree into a bunch of parentheses. So the verb phrase, we can enclose it into parentheses, brackets, into square brackets. The other verb phrase, we can enclose it into red square brackets, prepositional phrase into green square brackets, and the two bottom noun phrases into purple square brackets. So we can reflect this non-associativity by introducing explicit parentheses. And now comes a couple of operations which will actually help us a lot with capturing the grouping structure. And because why do we need to capture this? Well, large language models, just like they better know what the sentence means. So when there are these different parsings, they need to be distinguished. So the upshot is that the language generation is not just channels, which we have introduced so far, but also involve this bracketing, because different bracketings induce different meanings, and we need to know which meaning it is. So in this case, we need to go into semantics to ask ourselves, is it possible that the elephant wears Groucho Marx's pajamas, and we choose one of the two meanings as the actual meaning, and the other meaning remains in its impossibility as Groucho's joke? So we want to analyze this, and how do we do this so that we don't have to carry these trees on top of every phrase with us? Well, we introduce parentheses, and the other one, we can introduce the other parentheses, and you see that now it's maybe even better to see how the verb phrase. So on one hand, shot an elephant is separate from in my pajama. On the other hand, the elephant and pajamas are bracketed together. So now you see that the other parsing corresponds to the meaning where the elephant wears the pajamas. So what do we do with this? So let's take this bracketing, and we can link the brackets as references. So the first bracket from shot, when we're producing or parsing this sentence, we begin with I, and then we know that after that a verb must come. Since shot is a transitive verb, the question will be shot what? So the scope of Groucho's shooting is enclosed in the blue parentheses, and the reference to what will be shot is discharged only after this blue arrow ends, and it points to the scope of the verb shot. And then after that comes an elephant. The scope of the elephant, again, it could be just that the elephant just requires the article, but also in this case, elephant also has the preposition. Elephant is in my pajamas. So that is denoted by the red. The scope of elephant is the red arrow. And then when we begin with in, there is in what? What is the scope of in? It's my pajamas. The scope of pajamas is we need either an article or another kind of determiner. The determiner here is that it's my pajamas. The determiner for the elephant is the article. So we have now denoted the scopes of all words by these arrows. And they actually give you what they study as dependency grammars in linguistics. We can now move, those are not just mere relationship between the opening bracket and the closing bracket, but they're relationships between words. I kind of I kind of indicated that already. So first of all, the determiners are dependent on the nouns elephant and pajamas. So actually the relationship between the front and back parentheses is the relationship between the inside words, between pajamas and my, and between elephant and word. And then the green brackets are relationship between in and the proposition to which it refers, between in and pajamas. And the red arrow is the relationship between elephant and the preposition. The in is not the preposition but the noun. But I was leaping 2 sentences forward. The red arrow is the relationship between elephant and the preposition with the elephant, and finally, shot is a relationship with the object of shooting, the elephant. So now, what we have is what you probably remember, I hope, from programming as references, which you use in linked lists. In each of these cases, you can think of these word dependencies in a sentence as open references. Shot is referring to elephant. Elephant is referring to in my pajamas. On the other hand, elephant is referring to ant. So let's give names to all these references like you have them in every programming language. Every link will get a name. So let's call shot reference in shot Y, and it opens it with the left adjoint of the elephant. It refers to the elephant. So what we do now is we systematically assign names to these references. And I will explain what these underlining and overlinings mean in a minute. So now we have the structure of references, of syntactic references, which the words within this ambiguous sentence which link the words in these ambiguous sentences. So the ways each of the words refer to other parts of the sentence have now been denoted by these syntactic variables. And what we have, the tacit outside, the final bracket is always the bracket around the whole sentence, also is a reference of I to the verb which it shoots. So now what we have is under each of these words, we have the annotation by the reference variables. Each of them is either a target or a source of some references, some of them of multiple references. Elephant has 3 references. These references and their relationships by underlining and overlining are their syntactic types. We can do the same thing for the other phrase. So I'll just summarize it very quickly. So here's the different bracketing of the phrase where I shot an elephant and I was wearing my pajamas. And we can again have the relationships between the brackets, and we can transform them into references between words, and we can annotate these relationships by reference variables. These reference variables are the syntactic types of the word. So this is a much more productive form of syntactic analysis of a phrase, which actually deconflicts meanings also behind a large language models. But there is an important catch. We're not just doing a grammatical analysis here. So what are these? What do these syntactic types do for us? They are patterns of language into which we, and when I say we, I mean all language generators, including you and me, and large language models, we sample them to generate speech. So a noun, a transitive verb would be of type left Y, left U, and right K, right X, whereas a pronoun is just a vanilla type X, and a noun, the elephant, is receiving a reference and it is sending a reference into an article, and so on. So the important part here is that we have the underlying type system behind these abstract syntactic patterns, which we sample when we are communicating. So we probably went through this too fast to justify what I will say, but the miracle of you knowing that I have made a complete sentence when I finish the complete sentence, and you knowing that there is something to still come in my sentence before I have finished the sentence, is explained by this syntactic typing, from which the actual sentences which we make, which consist of words, are just instantiations from these types. So we have a type system. We have these syntactic types. A syntactic type is like a data type is numbers, and then a particular verb which one may use is obtained by sampling from this syntactic type of verbs to comply with a syntactic pattern of a sentence. That is how the bracketings on channel productions generate articulations of language. And the importance of this is not just that this is how we explain that the sentences come about, but that this kind of structure goes all the way up, and that this kind of structure also explains when we know that our conversation is coming close to a conclusion, and when do we know that it is still open and that the meanings have not been closed. All levels of referencing work the same. So you will know that this sentence is complete when all references are discharged. That's the simplest way. As long as there are some references which are still open, you're waiting for some dereferencing to take place. You know how this works in Python, and literally exactly the same mechanism of dereferencing turns out to work into natural language as well. Okay, so now if we fish out of everything that we have said so far, if we forget the words and if we forget the empty spaces, and if we fish out just the structuring in terms of balanced parentheses, we get something that in theory of formal languages is called the Dyke languages. They are the languages of balanced parentheses. And the crucial theorem, which is not easy to prove, and I'm not going to bother you with proving you, but the idea of it is that all context-free languages, and English, for instance, insofar as formalized by grammars, is considered to be context-free. Now, there are context-sensitive phrases, but most languages have been thought to be context-free until very recently. Dutch is context-sensitive, and then there is a language in Gabon which is context-sensitive, and in Mali, and so on. But most grammars studied through history have been context-free. Now it turns out that all of these grammars that we have been studying all these thousands of years can be decomposed into regular languages, which are like I hope you remember from your basic computer science what are regular languages. That's like grepping in Unix or in Mac OS X. You're forming regular expressions. It's the simplest language that you can form. For instance, when you're compressing files, zip algorithm is seeking regular expression in the file, expressions in the source of the file that you're zipping. So they are the simplest kind of algorithms. There are algorithms which can be implemented in finite state machines. All context-free grammars can be implemented as regular sublanguages of languages of balanced brackets. So there's a certain universality in this bracketing mechanism that we just demonstrated, and of course that universality means that Dyke languages are actually the free context-free languages. They are initial. For every context-free language, you can find a Dyke language and a regular language such that the language that you're talking about, say English or C, if we want a simple context-free language, is a homomorphic image, is a quotient of the regular sublanguage of bracketing. So we can generate all languages just by quotienting, pairs of brackets in the simplest possible regular way. So that's the message of this part about bracketing. And then one of the groups will have the exercise, which I'm sure all of you will enormously enjoy, of spelling out this bracket algebra. They are called Pregroups because these discharging bracket, it's like the weakened version of inverse. A group is, for instance, integers. Everything has an inverse, and every bracket has the other bracket. Left brackets have the right brackets have the left bracket. So first we have the monoid structure, which is just sequences, and then we have ordered monoids. Integers are an ordered monoid, for instance, and then we have these underlinings and overlinings, which give us these weak inverses, and we can do everything that we do in bracketing languages with that, and everything that we do in context-free grammars. So that's what we're going to hopefully rather quickly go through, but we need to have a good idea how this works, because that's a part of functioning. And these pregroups it's a very, when you get used to it, it's a very pleasant structure to work with, and it gives us a pleasant framework to analyze language production. So these two components, I claim, are sufficient to model language production. So what? Well, I kind of indicated already so what. So on one hand, I've proven by these examples that sentential syntax boils down to bracketing. So now the important part is that the same mechanism goes all the way up, not just to sentential syntax, but to relationships between sentences, to relationships between conversations, and to protocols. I have presented the syntactic types as these references under the expressions to point to the fact that the structure is just like protocols. So you're looking at the very high level view of this Laulima login two-factor authentication that we're all using. Alice wants to log into Laulima, and she asks her computer to authenticate her, and her computer sends a message to Laulima itself, and Laulima uses Duo to contact, and Duo contacts Alice's phone, and Alice's phone sends a challenge to Alice, and Alice then enters her, what is it? She says, oh yes, I own this phone. She pushes the button and says, yes, I confirm that I have control on my phone, and Duo says it's okay, and then Duo sends message that Alice's authentication succeeded to Laulima, and Laulima sends a message to Alice's computer, which unlocks the screen to Alice. This is the same structure, the same kind of bracketing, referencing structure as underlying the sentence. At all levels of communication, we have communication channels, and we have bracketing, and we have these. So sending and receiving messages, in this case, are these brackets. So the upshot is that to generate sentences, large language models are using this structure, channels and brackets. Moreover, to generate behaviors, which is what we're interested in when we want to think about security, they're using exactly the same structures. So the underlying space is modeled using the same tools. So the next word predictions, the miracle of predictive inference is next word predictions generate language. Next step predictions generate protocol runs. So in the same way in which I'm generating this sentence by sampling the type structure, the syntactic type structure underlying that sentence, in the same way, protocol runs are generated by sampling the syntactic type structure, which are the standardized protocols. Here we have an outdated diagram of the internet stack, but all protocols work like that. So the question that we're left with is whether deep neural networks can learn protocols by the same learning algorithms which have allowed them to learn language in the way we have witnessed. So that is the next level of the question of AI security that we're left with. And that's my talk. I'm going to stop recording first and then ask for your questions.